Hey guys, welcome back to another tutorial. Today we're looking at rocket propulsion with gravity. So if we go here, if we look at a rocket and we can see it like this, let's just draw it like this. Oh, sorry, that's way too thick. Let me just go on to there we go. Anyway, we'll go back to black. Let's just rub that out first. So yeah, if we look at a rocket like this, that's a brilliant drawing. Anyway, the gravity, we have the weight like this, mass times by gravity for the weight. And we know the velocity, it's moving upward like this with velocity, and it has this gravity pulling it back. Now, if we look at the system like this, we have the rocket first of mass m, right, and its velocity v, and then after dt, an infinitely small change in time, we get therefore the next system of where the mass is m plus dm, a change in mass, v plus dv, but we also have the fuel ejected. We have the fuel ejected there of dm. That's not very clear. We have fuel ejected, and that fuel is dm. Oh, sorry. That is dm, and that's being ejected. And that's got its own velocity of v minus u. Now, the reason that velocity is v minus u is because if we look at relative velocity, that's the velocity of the fuel. It's equal to now. Think of it this way: you have the rocket moving upwards, right? Like that. It's moving upwards with velocity v, but the fuel, like that, being ejected, is moving out at, let's say, velocity u. Now, relative to the rocket, it is moving at minus u from the rocket. However, we don't want to look at relative motion. We want to look at the absolute motion of it, and therefore it's going to be v, because it's with the rocket at first, minus the u, because it's being ejected at minus u, and therefore that's the velocity of the fuel. Now, if we want to put this into equations, one important area to look at first. One second. But yeah, we want to look at basically the momentum is really important here. So we know the momentum beforehand is equal to mass times by velocity. That's the equation for momentum. However, we have to also look at the external force. Now, the external force, like this, is going to be external force, ext for external, times by dt. The reason why is because momentum is rate of change force is rate of change of momentum. Therefore, times it by dt will get us the momentum that we need. And we know that we can actually, I'll show you what the actual external force is. The external force is equal to negative mg. The reason why is because we are resolving upward like this. The velocity of the rocket is going upwards. However, gravity is acting downwards. So therefore the force is going to be negative mg. Anyway, so we know one thing is true. If you look at any kind of momentum equation, we know that the momentum before is going to equal the momentum after. So the momentum plus the external force, is going to equal the momentum after. So it's going to be mass times by velocity minus mg times by dt is equal to, now the entire system is going to be mass plus dm, like this, v plus dv, and then we're going to add, and it's going to be minus dm by v minus u for the fuel. It's minus because the fuel gets ejected the other direction. That's why. So it's minus that it's being lost, the fuel from the system. So therefore you have the full system there. The momentum before, momentum plus the exterior force, which is negative mg dt, is equal to the new mass and new velocity. So basically the new momentum of the rocket, and then minus the momentum of the fuel, because again it's being ejected, it's losing it. Now, if we look at this now, what we can actually see is we're going to times it all out and collect terms. So minus m times by v minus mg dt is equal to, expand those brackets, so it's going to be mass times by velocity plus dm plus mdv plus dm dv, and then it's going to be minus dmv. Sorry, it's not very clear. Plus u dm. I apologize, it's not very clear there. But yeah, you minus dm dv, and then that. And what we're going to do is we're going to cancel. We can see that vdm, like that, is going to cancel out with their dmv. That's going to cancel out vdm as well. And we're also going to cancel out the mv terms. They're going to cancel out as well. And once you've done all that, you get it into this form, minus mg dt is equal to mdv plus dm dv plus u dm. Now we can get into a better form. Now we know one thing, dm dv is going to cancel to 0 because it's two infinitely small points times together. So we're going to approximate that as 0. It's basically negligible. It's so tiny we don't need to consider it. And so the final form is minus mg dt, like this, is equal to mdv plus u dm. Now this is the form we have now. Let's put it into a different format. Let's just rearrange it. So we have let's put the u dm on the other side, and we'll switch it around. So we'll have mdv is equal to minus u dm minus mg dt. So we have it in this format now. It's a nice format. Obviously for the next part, what we're going to do is we're going to divide by m first of all. So dv is equal to minus u over m times by dm minus g dt. So we have it in this format now. dv is equal to that. And if you want to, we can keep going with this. We can just divide everything by dt, so we can get it into a differential equation form. dv by dt is equal to minus u over m times by dm by dt, and then we see g divided by dt divided by dt is going to be g. So this is the form we have it in. This is a differential equation form we have it in now. So we want to work with that. Now, what we're going to make one assumption, because that's hard to solve. We're going to make one assumption to solve it. We're going to basically assume that dm by dt is constant. To simplify it, so we're going to assume that it's losing mass at a constant rate. So we're going to call it negative lambda. That's what we're going to say. We're saying it's losing mass at a rate of negative lambda. Now what we need here, we're going to rearrange it to get it into dm is equal to negative lambda dt, like this. And this is now, we can integrate this. This is a differential equation, an easy differential equation to solve, or we've done this before. If you haven't done this, I'd be happy to do a video on how to solve differential equations. This is a fairly simple differential equation type. With the integral between the initial mass and the final mass, or the current mass, and it's going to be dm is equal to, and we're going to have it is here, which again in there it's the same as 1, so that's going to be helpful when it comes to actually integrating it. And in here we're going to have negative. We'll take the negative outside the integral between 0 and t for lambda dt. And with that we can solve it. You can see it there, you can see the integral there. And we can solve that. We know that the integral of 1 for dm is going to just be m, and we know the integral of lambda for dt is going to be lambda t. So we solve it into this form here. Mass between m0 and m is equal to, we'll keep the negative number out, lambda t between 0 and t. And that's, we can very easily solve that to get it into format. That can be solved into format. I'll show you the form. So that's the form we get it into, as you can see, like that. Now, that is going to equal, if you've done integration before, it's just going to be mass minus m0 is equal to negative lambda t. And then we can get into a final format of mass as a function of time. Sorry, let's just change that. We'll put it somewhere more convenient. Yes, mass as a function of time. That's not helpful actually. It's not in a helpful area. Yeah, we'll put it underneath. So mass as a function of time is equal to the initial mass of the system minus lambda times by t. So it's linear. We've got a linear because we've basically made it linear to simplify things, because otherwise it'd be a lot more complicated. Now to solve this, we're going to put it back into our equation. So if you remember our equation form, like this, dv by dt is equal to negative u over m dm by dt minus g. We can put that into that form. So we get into the form, we're going to get dv by dt is equal to, look again, negative u over, and for m, remember m is just is mass as a function of t, so it's going to be m0 minus lambda t, like that. And then by the way, dm by dt is equal to negative lambda. Remember we defined it earlier. See, we defined that. So to make it simpler, we have dm by dt is equal to negative lambda. So that's just going to be times by negative lambda, like that. And then minus g. And this can be written out into the final form as dv by dt is equal to u times by lambda over m0 minus lambda t. Sorry. Because it's times by lambda, and then minus g. So you can see this is the format we have it in now, and this is an equation we can actually solve now. This is a differential equation that's a lot easier to solve. If we just put the dt to the other side, we can solve it. I'll show you. So if we get into this format, dv equals u lambda over m0 minus lambda t times by dt minus g dt. This is now an equation we can actually solve. So let's do, or at least a lot easier to solve. So let's just do the integral between the initial velocity of the system and the current velocity, dv, is equal to, and we'll take up the factor of u and lambda, so u and lambda, as they are both constant, and we have here the integral between 0 and time for 1 over the initial mass minus lambda t dt, and of course we have the final part, which is minus the integral between 0 and t of g for dt. Sorry, I don't know why that happened. Like this. That's not clear enough. There we go. So you have this now, this integral form, and we can integrate them all. So, and we know how to, we've done integration before. We know how it's going to work. We're going to get it into form of v minus v0. We know that because we know the integral of 1 is v, and it's v minus v0. Let's make it clearer. We showed that earlier. So v minus v0. Oh, I need to move down a little bit. Sorry. When you're writing integrals, they do take up a lot of space. It's one of the problems with it. Even that's too much space. I apologise for the technical errors. V minus v0 is equal to, yeah, that's better, is equal to, yes. Now the integral of 1 over m0 minus lambda t that's going to be the natural logarithm. That's going to be a natural logarithm. I'll show you what it turns into. So you've got u times by lambda, And then in there, we're going to have, in brackets, we'll start the brackets here. It's going to be the natural logarithm of, now, m0 minus lambda t, like that. And then you apply the chain rule, and you're going to get, you get the chain rule, and you're going to end up times them by negative 1 over lambda. That's the chain rule. If you haven't done the chain rule, I would recommend looking that up. A lot of mechanics will eventually use a lot of calculus. If you haven't done it already, yeah, a lot of calculus is used in mechanics, to be honest. The reason why, when you differentiate that, you're going to times by minus lambda, which is going to cancel out that term. But that's basically, the chain rule is really important in a lot of maths in general, but you're going to get it a lot in mechanics, to be honest. So it's definitely worth learning calculus, learn integration, learn the chain rule, learn differentiation. This is going to really help you in mechanics, because it's all about, when you look at dynamics, which is all about motion, and acceleration and velocity, there's so much calculus involved there. So, and then for G, it's just going to be minus, it's GT, T, and then 0, so it's going to end up becoming, like before, GT. So we have it in this format now. Now, what we can do now is we can take that minus lambda over 1 over t for 1 over lambda can be taken out as a constant. We don't have to keep that in there. So we can turn it into v minus v0 is equal to, and then the lambda can go like this, so it's u lambda, and we take the negative 1 over lambda out, so dot 1 over lambda, like that, times by, sorry, it's not very clear, it's 2, again, I keep forgetting how much space integrals take up, so it's v minus v0 is equal to u lambda dot negative 1 over lambda, and then it's going to be, now when it comes to ln of m0 minus m lambda t, like that, I'll make it clear for you, but that's going to be ln of, again the big brackets, ln of m0 minus lambda t, like that, minus ln, now when time equals 0, it's going to cancel out and you're going to be left with this. You're going to be left with that. Because, when you times out, you're going to be left with that, obviously, because the t is equal to 0, so you get into that form. And then minus gt. Now, that's been put there. To finally solve that, what we want to do is what we want to do to finally solve it is we want to flip that around. So we're going to get into v minus v0 is equal to, and let me just write it out. I want to quickly show you what's going to happen. Because we have like this, I'll show you. That lambda is going to cancel out with that, and that negative there, that minus sign is going to flip these around. It's going to flip these to ln of m0 minus ln of m0 minus lambda t. I'll show you here. So you get it into final format of u, and then it's going to be, that negative is going to flip them around, so we don't have to worry about that. It's that and times by the bracket there, ln of m0 minus ln of m0 minus lambda t, like this, minus gt. And then for the next part, it's going to just be, if you're wondering, ln of m0 minus ln of m0 minus lambda t, in natural logarithm, in logarithms or logs in general, that just becomes, basically, I'll show you, that becomes, so v, let me just make sure there's enough space, v minus v0 is equal to u times by ln of m0 over m0 minus lambda t. And then minus gt. So we've got it into this format here. This is the equation we've got. This is the format we've got it into. V minus the initial velocity is equal to u lambda, the natural logarithm of m0 over m0 minus lambda t, minus gt, which you can get into an even nicer form of v is equal to the initial velocity. Actually, let me just create space again. V is equal to the initial velocity plus the natural logarithm of the initial mass. Now we know that m0, the initial mass minus L lambda t, is what was equal to, do you remember earlier, it was equal to that the function of time is equal to m0 minus lambda t in the way that we defined it. So what we can do basically, like this, we can get it into, we can just call it m, the function of m, like this, minus gt. So as you can see, we've solved it. We've got the equation now. That is the equation now with the gravity that we have for the propulsion. That's the velocity. Velocity as a function of time. You know, v is equal to velocity as a function of time. So we now know the equation of vt as a function of time is equal to the initial velocity add the natural logarithm of the initial mass over the mass as a function of time. Remember that m is mass as a function of time. We also, we know that we can define that mass is equal to mass as a function of time. And that's solved. That's the final form you get it into. And that is propulsion of rockets with gravity in one dimension. We may look at 2 dimensions in the future and maybe even 3 dimensions, but for now, 1 dimension does make things simpler. But yeah, thank you for watching, and consider subscribing. Thank you. Bye.